lazım download edilen bir yerler. Sonra demiştim. Bak bir saat karşılığında var. Yok bir saat değil. Yani download edeyim istemez. Download edilebilir. Ele tam alması olsun. Gitmesin ha. Tam ekran. Tam ekran öyle. O ne derim? İstemeseydi. Tam ekran. Şimdi bu sertifikadan nasıl bir bağlıyız? Solu bağlı. Ben tarafa döndürme olarak belli olsun.
Next speaker is Nosratollah Jafari from Besenkov Astrophysical Institute Almaty and Center for Theoretical Physics Khazar University. Non-relativistic limits of Klein-Gordon and Dirac equations in the Amelia W special relativity. Please.
Hello, thank you. Hello to everyone. It's working. Hello to everyone. I am very glad to speak in my second land, Azerbaijan, and very happy to participate in this conference. And thank you for Şahin Muallim, Farid Khanum, and Behnam, every organizer of the conference, and Khazar University. Thank you. My talk is about the non-relativistic limit of Klein-Gordon and Dirac equations in the double associativity. Amelia double associativity is the first one double associativity and is the well-known. With this, I want to excuse me, let me to introduce the double special relativity. If we look to the Einstein equation, the first equation of the special relativity boost is the one equation. This equation is for the boosts. We have I, PA, rho to partial derivative of E plus I is the imaginary, E, partial derivative with respect to PA. And this equation is the essence of the special relativity. In double special relativity, normally we are introducing another scaling and Planck scales, and we are modifying the special relativity. Instead of no, İsterim ki yetmeğin burada cursor yoktu. Yani aşağı yukarı eleme olsun. So let's us to start from the non-relativistic in the special relativity. In special relativity, we have the 7 equation is between the energy and momentum. We have E square minus P square equal to M square C4. Usually we say that C is 1. In the non-relativist limit, when the energy of the particle is when the momentum is less than energy, or in otherwise P2C2 on M2C4 is very, very small with respect to the 1, we can obtain the equation 8. Equation 8 is the square of the P2 plus M2, and the result is MC2 plus P2 on 2Ms. MC2 is the rest mass energy, and we can neglect it in the non-relativistic limited. And P2 on 2M is the usual Newtonian expression for the energy. So the essence of the double associativity is modifying from the equation. We have speaker. In special relativity, we have equations 7. The essence of double associativity is going from the equation 7 to equation 9. Equation 9 is a modified dispersion relation. Is it the standard relativity? We have adding additional term like this, P2C2 on K, E. K is the Planck energy. It's very, very huge energy, 10 to 26 giga-electron volt. So I want to do again equation 7, equation 8 for the modified dispersion relation equation 9. In the usual, we have equation 8, and we have base mass and energy. So in equation 9, we have additional energy, P2C2 on kappa or K is the Planck energy. So for finding this, we can go from equation 9 to equation 10 and solve this second order algebraic equation.
So one question, excuse me, what physical meaning of plus minus? This is particle and antiparticle.
In equation 8?
Yes.
Yeah. Before the limit, before the taking the non-relativistic limit, it is for particle and antiparticle. This is very important for us because with equation 8, we know that the plus sign is for the particle and the minus sign is for the antiparticle. This is the method that the Dirac for the first time introduced. So if we go from equation 9 to equation 10 as an algebraic equation, second order equation, then we have E equal P2. I can omit all C's. You can don't please see the C. C is a 1. P2 on K plus minus radical P4 on K2 plus 4 P2 plus M2 on 2. In the non-relativistic,
sorry, how arise K in equation 10? If you get
K, parameter K, we have introduced parameter K from the approximation of the Amelia-Camelia DSR. In Amelia-Camelia DSR, in Amelia-Camelia DSR, dispersion relation is the equation 2. cosinus hyperbolic E on K, min high cosinus hyperbolic minus n cosinus hyperbolic NK is over P2E. E exponential energy on kappa. And if we approximate this equation in the first approximation of the 1 over K, in the first order, second order, third order, we can obtain equation. Let me show. From equation 2, you can reach to equation 9. Equation 9 is the approximation of equation 2 in the first order of the 1 over K. Because K is very huge, and you can approximate 1 over K. And we neglect 1 over K2, K square. So instead of equation 7, we have equation 9. And
What's the physical meaning of the K is parameter?
K is the Planck energy.
Planck energy.
Yeah.
Oh, I see. Okay.
I'm introducing quantum gravity here because in the normal Dirac equation and Klein-Gordon equations, you have not gravity. By introducing K into the theory, kappa Planck energy, you are trying to have quantum gravity. So equation 10 or equation 9 is a modification of equation 7 and equation 8. So in equation 10, you have these radicals. In the non-relativistic limit, P is very small with respect to rest mass. And we have small energies. This term is the energy. Yeah, this term is the rest mass energy. So in the non-relativistic limit, from equation 10, we reach to equation 11, P2C to K plus minus MC2 in parentheses 1 plus P2 on 2M2. So we have also here, as Professor Shahin noticed, we have, he said, for the first time in this talk, we have plus and minus, and plus is for the particle, and minus will be for the antiparticle. But please pay attention here that in the Dirac equation, in the normal, in the special relativity, in equation 8, the energy of the particle and antiparticle is equal. But here I will show that the energy of particle and antiparticle will be different. Because here we have, and if we do 11 with negative sign, then the energy of the antiparticle will be another value. And for first time after modern physics, after 100 years, we can say in quantum gravity that the particle and antiparticle can have different masses. In the normal standard model, the mass of the particle and antiparticle, for example, positron and electron, or proton, antiproton mass are equal. Please ask your question from me. Azari diyebilirsin, ben Azari. Excuse me for Azari. I can understand Azari very well because my mother tongue is Azari. Dokuzuncu tənqidlə 7-ci tənqidin fərqi fəqət budur ki, 9-cu tənqiddə o P2 C2 bölünsün K i var. O ancaq burada gəlir enerjinin adı pozuru. Partikel antipartikelin kütləsi fərqli olur.
Kanunda Planck sabiti kimi
Planck sabiti buradan gəlibdir. Yəni mən onu izah eləmədim ki, hardan gəlibdir, çünki uzun olardı. Deyirəm ki, gözünüzü bağlayın. Baxın, görün ki, 7-ci mən tənliyi götürmüşəm. Birdən demişəm ki, mənim tənliyim 9-dur.
O K var orada olduğuna göre biz diyebiliriz ki bu kvant gravitasiyası.
Bəli. Kapaya göre gravity gelir. Çünkü normal Dirac tənliğində gravity yoktur. Kapada hem H var, Planck, hem C var, ışığın sürəti, hem G var, gravity. Yani burada ben kapayla Planck enerjini getdim. Excuse me for speaking in Turkish, in Azeri.
Thank you.
I can continue. So, imagine that we have equation 9 instead of equation 7. Somebody, for example, a messenger from God, said that, oh, dispersion relation is not equation 7. This is not correct. The correct dispersion relation should be equation 9. So, if we do the same calculations from equation 7 to 8, we can repeat the same calculation from equation 9 until equation 11. So the interesting matter is this: equation 11 is different from equation 8. In equation 8, we have equal energy for the particle and antiparticle. But in equation 11, we have different values for particle and antiparticle energies. So this is the first experiment. We can have an experiment. If we can detect different masses for particle and antiparticle, we can discover quantum gravity. Quantum gravity is the main discovery. People are searching for 100 years for that. So let's go to another equation. Equation 12 is the equation for the particle, for example, positron. And the positive sign here, positive sign is for the particle. So we can introduce m plus is equal m on 1 plus mc2 on k for the particle, and m minus is equal m on 1 minus mc2 plus on k for the antiparticle. So you can see that the mass of the particle here and the mass of the antiparticle, equation 14, is different. And this is very interesting result. So let's check how can use this difference. So for particle and antiparticle, we have different masses. So we can obtain equation 16. Equation 16 shows that m minus m plus minus m minus on m minus, the difference between them, the fractional difference, is in proportion with 2m on k. Let me to show that. If you pay attention here, for m plus and m minus, they are proportional to mc2 on k. So my expectation is this: the difference should be a fraction of mc2 on k.
Just one question, excuse me. So how do you, so the previous page, please.
Bundan gelir gelir aşağı.
Aha.
Buyur.
Equation,
Please.
you wrote the dispersion relations which contain k.
Yeah, I can come back.
Well, yeah. Equation 2.
Equation 2. Yeah.
Yeah. How do you obtain it?
This is a little bit complex. In Amelie Camellia, I will show you DSR. let me to show you. This is the modified boost. Equation 1 is the boost. Equation 1 is this like this. We have I, E, and I will show you the equation 1.
Just, excuse me, what,
Let me show you. This is the normal boost.
boost, okay.
Yeah, this is the producer of the
Yeah,
Poincare group or Lorentz group. This is the boost, normal boost. If I add something proportional to the Planck energy, I am modifying the boost. So we are modifying the boost 1 from equation 1 to
so just this modification is equivalent to modification of space-time, isn't it?
let me, just a moment. We are modifying equation 1 to equation 3. And from equation 3, we can obtain cosinus hyperbolic, the second relation.
But I am interested, what physical foundations of this modification?
Physical foundation is this. A double associativity has obtained from the Kappa-Poincare. And Kappa-Poincare dates back to the 1980 decades or 1970. And Kappa-Poincare is the extension of the Poincare group. By adding a parameter like kappa can be Planck energy or this K. By adding one parameter, we are extending Kappa-Poincare group. And this boost, modified boost, has obtained from there, from extension of the Poincare group. And the philosophy is this. In 4 dimensions, we have only Lorentz group. Lorentz group is in 4 dimensions is the best group for the physics. We cannot find another group. So we are going to modify the group by adding an additional constant like kappa. So we have modified 3. If you accept that, this is my modification. Or you can say that, oh, I don't want to think about the boost. I am saying that instead of equation, instead of equation 7, some messenger from God can say that equation 9 is correct. And equation 7 is the low energy effects. And the true and the correct form is equation 9. So forget about the boost. Somebody can say is that we can start from equation 9 if we do the same procedures for finding particle and antiparticle. Particle as antiparticle created from the Dirac solution of the Dirac equation. But first, he did that if we use this particle, this square, we can obtain plus and minus. This plus and minus is the heart of the particle and antiparticle. So we have different masses. Let's go to the second slide. So we have different mass for M plus and M minus. M plus, for example, you can assume that is the electron. M minus is the positron. So we have equation 16, M plus minus M minus on the fraction is in proportional to M on kappa. So for electron, we have equation 11. 2m electron on kappa is 10 to minus 22. If we can find very hard particle, very strong particle, very massive particle, because electron is not so massive. Unfortunately, we cannot until now in the experiment very massive particles. For example, tau. This fraction can be good. 10 minutes. And this is the difference between positron and electron masses. But in the particle data group, as you know, that particle data group is the best group for the measuring the particles masses. This fraction is 8 times 10 to minus 8. So, because quantum gravity effects are usually very small, we can say, we can have quantum gravity. But this is not absolute. This is not discovered. Only a probability. So, we can obtain this fraction. And what about then? What is the consequence of quantum gravity? What is the consequence of introducing kappa there? Is there something beyond the standard model? In normal standard model, the photon mass is 0. Everybody knows this. But in this scenario, in quantum gravity, the photon can be massive. If we do some calculations, we can reach to equation 9, and this shows that photon can be massive. And the difference of these masses, m plus, m minus, the difference between particle and antiparticle can be related to the photon mass. And this is the relation. I don't want to show the detail of the calculations. So we can obtain here that mass of the photon here can be 2.5 multiplied by 10 to minus 18 electron volt. Very, very small mass, but it should be massive. If we have quantum gravity, it should have massive photon. So also we can obtain a bond on kappa. You have some question about the kappa. So kappa in my calculations is bigger than 1.1 times 10 to 18 gigaelectron volt. Normal value for the quantum gravity is 10 to 19. But we have a bound on that. Kappa should be bigger than this value. So let me go to have some discussions. There is a very well-known theorem about the standard model, and this theorem comes back to Pauli in 1916 decade, 50 decades, 1950, 1956 years. And this is the well-known theorem that a standard model should have CPT symmetry. CPT is, C is the charge conjugation, P is parity, and time is time reversal. All the standard model should have symmetry with respect to this. But in quantum gravity, we are going to have some valuations of this symmetry. And this shows that we have Lorentz symmetry breaking, or we have non-local theory, or we have another, for example, non-commutative models. Here we have Lorentz symmetry breaking, because double special relativity have some Lorentz symmetry breaking. So let me to show the non-realistic limit or of the Klein-Gordon and Dirac equations. Equation 26 is the normal Klein-Gordon equation. And if we introduce m as a square of m2 minus del 2, we can do some approximations and we can reach to equation equation 33. This is very similar to the Schrödinger equation, but before that, I am reaching to the equation 31, and this is the approximation of the Klein-Gordon equation. This is normal in quantum. This is normal in quantum field theory books, and you can reach from Klein-Gordon equations to the Schrödinger equation. I am looking for quantum gravity part, for DSR part of correspondence of this. in DSR, the modified Killen-Gordon equation is this. We have additional term. So this is the modified M.
So, excuse me, you add this term, modification term by hand or?
No, this modification term is from boost and is from the
Okay.
dispersion relation. If you have only one deform,
Understand.
let me. If you have only one modification, for example, in dispersion relation or in boost, every equation should be modified.
Yes.
So we have modified M, and we should reach to modified Schrödinger equations. Modified Schrödinger equation is 46. Let me show for Dirac equation because we don't have so much time. Dirac equation normal is equation 41, and we have normal procedure for the non-relativistic limit. In the limits, we have equation 45. So I want to show you modified Dirac equation. Modified Dirac equation is 47. You have also in your poster, in your talk, the first talk, some modified Dirac equation. We can do the same for that. So this is the modified Dirac equation. Only this term is modification. This term. So I am looking for the non-relativistic limit. And the non-relativistic limit is like this. And this is the modified Dirac equation in the non-relativistic case. But for saying some things, let's to come back to the not to Dirac equation or Killen-Gordon equations. I showed that Dirac equation can be modified. Dirac equation is the heart of the particle and particles. With Dirac equations, we know that there is particle and antiparticles. Because of this, I showed that there is modification in the Dirac equations. So let me to come back to the second page. This is very important page. Here. Everything is here. We have normal boost. This is the special relativity. So instead of boost 1, we have boost 3. And for equation 4, I didn't show you before. This is the modification of the Dirac equation, Killen-Gordon equation in double special relativity. How much I have time? 2 minutes. So here, I am discovering a new, very interesting things. I can say another things. I can ask a question. Can we find a universe that have, after particle and antiparticle, a new type of particle? Why we only have antiparticle? What is the basic of this? The basic of this reasoning comes back to the equation 8. If we have, instead of equation 7, if we have a third order equation, we should have a word like this. We have particle, antiparticle, and some new kind of matter. And I gave to its name quantum gravity particles. If we have third orders or fourth orders, we have some symmetric rule, and we should obey this. But if we can modify equation 7 to equation 9, so we have different masses. And beside that, if we have, for example, for equation 9, if we go to another approximation, we can have fourth order. or E3. So maybe in quantum gravity, we can say that plus to the particle and antiparticle, maybe we have in very, very high energy universe, another type of matter. This is maybe interesting, but this is not discovered.
I would be interpreted as a particle and antiparticle shows different properties at quantum level, quantum gravity levels.
Yeah.
Yeah.
Thank you. And because of this, I stress about this page, because this page is the heart of my talk. And let me to show just one minute. Question 13 and 14. And I say that if we have third order, this is very interesting. Dispersion relation in the world, we should have particle, antiparticle, and a new type of matter. Thank you for this.
So we gave a lot of questions during his talk. Is there any questions?
Yes, I have. In equation 19, we said that
19?
yes.
19, let me to go.
Photon mass. Isn't it problem for the polarization, photons polarization, and it can be modified the polarization of photon?
You are asking about the polarization? Yeah, we should have, for example, in photon, we have only two polarizations.
Yes.
If we have mass, we have additional polarizations.
Yes, three polarization states in the case of mass. Okay, yes. You öğrettiğin Azerbaycanca mı?
Azerbaycan'dan bilirim. Sorry for speaking Azeri, but I should go. Yeah.
Siz beni bir geç geldim. Ben bir başa düştüm ki relativistik nedeni modifikasyon edilsin.
Bəli.
Bunun fizik esasları nedir? Niye modifikasyon edilsin? Nereden çıktı bu?
Aha,
Neye sebeplendirsiniz?
Azerice konuşa bilərəm konferansda. Ha, bilirsiniz bu hardan geldi? Bu buradan geldi ki 70-ci və 80-ci illərdə 1900 cəmaət bu nəticəyə çatdı. Yəni bir dənə qəziyyə orada sübuta yetirdi, qəziyyə teorum. Fars dilində deyilə qəziyyə teorum. Bu teorum bu idi ki, 4 ölçüdə Poincaré qrupundan böyük qrup yoxdur. Amma əgər biz istəyək quantum gravitini ələ keçirək, görək ki, yüksək enerjilərə baxaq. Yüksək enerjilərdə Planck lenti görək ki, eləyək onu əsas. Yəni bu ki, biz string theory'dən, başqa yerlərdən bilirik ki, kuantum effektlər,
Sual veren yedi şekil çekti.
kuantum gravity effektlər Planck lentdə olur. Planck'ın uzunluğunda olur. Amma Planck'ın uzunluğu əgər sabitdirsə, ondan contraction'la biraz problem olur. Yəni Lorentz contraction vardır. Bir cisim ki, işıq sürətinə yaxınlaşır, onu uzun ya qısa görürük. Əgər transition klassik gravitydən quantum gravitydə olsa Planck lent 10 üstü mənfi 34'dür. Ondan, əgər special relativity olsaq, bunu başqa görəcəkdir. Yəni biri görəcək 10 üstü 34, mənfi 34, biri görəcək mənfi 32. Ona görə gəlirik, deyirik ki, bir saniyə. Quantum gravity görə ki, gələ bir model düzəltsin ki, orada Planck lent sabit olsun. Double special relativity oradan əmələ gəlir ki, deyirik bir dənə başqa sabit ki, Planck lentdir, mən gəlirəm special relativity əlinlə qoyuram.
Burada fundamental dilin uzunluk olacak mı? Fundamental length.
Fundamental length elə Planck lentdir da. Planck'ın uzunluğu. Bəli, bəli. Onu mən əllə gəlirəm, əlavə edirəm.
Kvant gravitasiyasında bunu daxil etmək mümkün olacaq mı? Siz belə başa düşün. Gravitasiyada
Gravitasiya Planck lentindən gəlir də, çünki Planck lentin içində gravity var. Planck lent nədir? Oldu.
Çok sağ olun.
Thank you.
Ayrıldı.